Did you already complete the square? What's going here? 1. -2 divided by 2 is -1. When you square it, you get 1. Did we just add 1 to the left side? We added 9. How about the x's? Bless you. We need 9. Did we just add 9 to that side? Oh, in fact, we didn't add it all, did we? We did. -4 times 9. Subtracting 36. So let's see what this big mess looks like once we've done our addition and subtraction on that. So, what do you get on the right-hand side? Oh, that's a good number. I like that number. So now what do we do? Exactly. People remember, we've got to get a 1 over there, and that's the way to get rid of that 9 and that -4 there. Dividing everything by 36. Whew. We proved it. There was more. Prove that the graph of the equation is a hyperbola. Find its vertices, foci, and asymptotes. Well, all right then. Well, we probably better graph a little bit of this then. Where is its center? Uh-oh. 1, 3? 3, 1. Good catch. Horizontal or vertical? Vertical. How far up and down? 2. And again, you, without graphing, this didn't say we had to graph it. If you can remember, okay, if I'm doing this vertically, that means that my y's are going to be changed here. So I'm going to have to add and subtract 2 from my y's. Get your 2 vertices that way, but the sketch certainly does help. All right, so now we've got the vertices on there. We were also supposed to figure out the foci. How do we get that again? A squared. Go on, c squared equals a squared plus b squared. Good, that was the part I was waiting for there. Well, we had a 4 and a 9 when we did our a squared and our b squared here. So that's going to give us 13. C is the not so fabulous square root of 13. Is that affecting our x's or our y's? Still the y's, exactly. Whatever a did is what we have to do for our foci. So we had a nice little center of 1, but it's going to have to go up the square root of 13 and down the square root of 13. So we'll have 3 and 1 plus or minus the square root of 13 for the foci. Now, here comes the weird one. The asymptotes. Yeah. So, would it be a bad idea to go ahead and graph it so you can think your way through it? You know, we do have that 9 still there for those covertices, which again the book does not call covertices, but that's what they are. And since we had this nice long weekend with fishing opener and Mother's Day in there, we absolutely don't make a little ellipse out of that. What do? The box. That's the thing you have to kind of pause and say, okay, wait a second. What did I do here? I don't want to accidentally make that ellipse. What's the box for? Oh, most of you had prom too. Good gravy. What a packed weekend. Wow. Fishing opener, prom, Mother's Day. It's packed. All right. Were we supposed to go up and down with this or side to side? Up up and down, this was a vertical. Okay, now why does that help? Because I want to think through those asymptotes and think, okay, from my center, how would I get to this asymptote position up here? Well, I'd have to go up A and over B. Oh, yeah, that's what it is. Y equals plus or minus A over B. X. Unless it's not centered at 0, 0. Is it centered at 0, 0? And notice how the X minus H is in the parentheses because we're always making sure people know, hey, we've got to group this stuff together here. So, plus or minus, if A squared is 4, that means A is? And if B squared is 9, that means B is 3. And I scrolled up too far. What was it again? 3, 1? Yeah, there it is. So, asymptotes is a little messy. You know, you have to think through the steps, but not necessarily memorize. Remember, it's not about memorizing. It's about understanding how the conics work so that all the pieces will come together for us. So that's what we've got to do with that one. Now, did we do everything? Did we find the equation, the vertices, the foci, and the asymptotes? Cool. We even graphed it. That's a bonus there. So on the next page, this is where we're going to talk about that part of your objective, which has to do with the applications. Kepler's first law of planetary motion says that a planet's orbit is elliptical with the sun at one focus. Makes sense. Since 1609, astronomers have generalized Kepler's law. The current theory states a celestial body that travels within the gravitational field of a much more massive body follows a path that closely approximates a conic section that has the more massive body as a focus. So that's the reason that the sun would be the focus. It's a much more massive body than the Earth is. And two bodies that do not differ greatly in mass, such as Earth and the Moon, or Pluto and its moon, Charon, actually revolve around their balance point or barycenter. In theory, a comet can approach the sun from interstellar space, make a partial loop about the sun, and then leave the solar system, returning to deep space, slingshotting around it. Such a comet follows a path that is one branch of a hyperbola. But in theory, we hope that never happens in our solar system. You don't want a big comet coming from outer space and slingshotting around the sun because it might decide to slingshot right into us. So we'll just watch that happen in other solar systems. Thank you very much. Reflective property of a hyperbola. Like other conics, a hyperbola can be used to make a reflector of sound, light, and other waves. If we rotate a hyperbola in three-dimensional space about its focal axis, the hyperbola sweeps out a hyperboloid of revolution. We talked about the ellipsoids of revolution. If a signal is directed toward a focus of a reflective hyperboloid, the signal reflects off the hyperbolic surface to the other focus. And figure 8.29 right down here. Light reflects off a primary parabolic mirror toward the mirror's focus, F of P equals F of H. So right here, little focus point. And which is also the focus of a small hyperbolic mirror. The light is then reflected off the hyperbolic mirror toward the hyperboloid's other focus, F of H equals F of P. Here, which is also the focus of an elliptical mirror. Finally, the light is reflected into the observer's eye, which is at the second focus of the ellipsoid. If you ever get a chance, and I know, Math Geek, they had on PBS a movie about the Hubble telescope. Now, you guys might have been too young when we were talking about this. Massive amounts of money, billions of dollars spent on the Hubble telescope. They put it up there in space. They hit the button. Billions of dollars. NASA was in huge trouble. We spent all this money. You told us we'd be able to see this stuff. Where is it? So, at NASA, they practiced changing all the mirrors on Hubble something had happened where one of the mirrors had gotten jarred and had gone out of position. They knew exactly what the problem was, and it was literally millimeters that things had to be moved. So they had astronauts in gravity-free space practicing how do we move this, how do we replace this, what do we do, and they actually sent them up there, and they were able to replace and retool the Hubble while it was still in a space that we could reach it, and they fixed it, and it was a huge deal. So, like I said, you're probably too young to remember any of that, but search it, Google it. Very cool movie about the different things that they had to do to make the math work, and that's the reason we're showing you this. Things don't always work perfect in Wi-Fi. I know we probably had perfect lives up to this point, but every once in a while something goes wrong and it's huge, and somebody has to know how to fix it. And we are actually talking a little bit about space stuff here, so pretty cool. So now what we have to do is we got to work on that completing the square stuff a little bit more. The people that I've been hearing from in class seem to be about the same people every time that are telling me what to do with that. So I want to make sure that even the quiet folks know what they're doing, are done. If you want to, you could go back to your spots, but you could also just stay and work where you are too. If you have your notebook and all that, whatever you want to do. And I will leave the answers up here